All right, so we got some serious mathematical business to take care of this morning, so I dug out a whiteboard. I'm not sure why the Toby household would have a whiteboard and expo markers around, but we do. We have some around, and so I thought this morning I would try and give you a little bit of an explanation of what exactly is going on. So the idea here is we're looking at functions that maybe go up and down. This one just happens to be entirely above the x-axis. We'll call this f of x. And our objective in this problem is going to be, we would like to find the area between point A here and point B that is trapped below the curve f of x and above the x-axis. So there's this bounded region here. There's a curve on top, x-axis on the bottom, and then we've got lines on either side. So we've been using rectangles to approximate what the area would be. So now if we say that we are going to want to have n intervals here. We're going to want to have n rectangles, so n is going to represent the number of rectangles to use for our approximation. Okay, so the width of each rectangle is going to be the total width of the interval. So I'm going to take b minus a, and I'm going to divide it by the number of rectangles that I want to use. So let's say like a is equal to 1 and b is equal to 10. So the difference between those two numbers is 9. If I take 9 and divide it by the number of rectangles, it tells me how wide each of those rectangles would be. Okay, so really what we're looking at here is for each one of the particular rectangles that we have, we're going to have to figure out a height. Okay? So on my first interval here, okay, so this is the first interval. Okay? On the first interval, I'm going to select some point on the interval. Now we've been using left endpoints, we've been using right endpoints, we've been using midpoints, but you could literally take any one of the points on that first interval, okay? Figure out what the function is equal to at that particular point, and then that's going to make the height of that rectangle. Okay, so again, I'm picking some point on the interval, evaluate the function, at that point to get the height. Now since that's the first interval, we're going to say that that point is x1, we'll put a little star by it too. It's x1 star. It's starred because it's the most important point on that interval. So the height here is going to be f of x1 star. Okay? If I want to find the area, then the area is going to be the width of the rectangle, which we're saying down here is this b minus a over n. We'll call b minus a over n, we'll give it a title of delta x. It's like our change in the x. So this is the width of each one of these rectangles. I'm going to multiply it by what the function's equal to at that point. Now I'm going to do that for each one of these intervals. So on the second interval, I'm going to pick a point. Doesn't matter where it is. Could be the left, could be the right, whatever. the height there is going to be f of x2 star. It's the star point. It's the second point that is exciting, interesting for us. Okay, and so that area is going to be delta x times f of x2 star. In fact, I could go on any one of these intervals here. We'll say on the ith interval. Ith is one of the greatest phrases to say here. Like it's great. It's the ith interval. On the ith interval, the area of the rectangle is going to be delta x. It's always delta x for the width of our rectangle here. And we're going to have f of x sub I star. Okay, so whatever the function's equal to at our special point on it. Now the idea here is if we add up all of these different areas of the rectangle, we're going to get an approximation for what this total area is equal to. If we go a little bit better here and we say that, hey, we're going to take the number of rectangles and we're going to make an infinite amount of rectangles. Now we can't really do that, but we can look at the limit as we make an infinite amount of rectangles. And we're going to add up all of those. That's going to get us not only an approximation, but that would get us the exact area underneath the curve. Okay? So let's take a look at like what that would look like if we wrote it up. Okay? So summation symbol. Okay, might remember that from pre-calculus. We're going to go from 1, we're going to start at the first interval, to n. So we're going to add up all of the areas. We want to add up all the areas. So to find the area each time, we're taking delta x, and we're multiplying it by f of x sub I star. Okay, so again, this is the area of each rectangle. This is telling us to add them up. And then out front of this, we want to do the limit as n goes to infinity. It's telling us, hey, let's make an infinite amount of rectangles. We can't do that, right? That's just like nonsensical. But we can look at the limit of what would happen as we go there. Okay, now this is where it ties into this weird new symbol that you're maybe starting to see. This is equal to the integral from a to b of f of x dx. Okay? So for right now, our integral is representing this area between a and b that's trapped underneath the curve and is bounded by the x-axis. Okay, so this integral is the limit of the areas as we get an infinite amount of rectangles. Okay, this is kind of like the theory behind it, and what we're attaching right now is this symbol to a physical quantity. We're using it to represent an area. We're talking about it in that term. In a second here, I'm going to show you how to figure out like that integral and some strategies, some rules for doing that. But this is like the background theory on why this is working.